you very much. I would like to thank the organizers for inviting me to this conference. In fact, it's probably the first time in my life I speak in such a big room, so I apologize for my possible shortcomings. So my talk is called Perverse Schobers and Applications, and let me change the paper. It takes a few moments to adjust. It's based on a series of joint works, some of them in progress, with Alexei Bondel, with Zickerhoff, Vadim Shechtman, and Janssen. So, first of all, it's better. First of all, let me say a few words about the term shopper. So, what really we are talking about are categorical analogs of perverse sheaves of categories. So, usually the word or sheaf of categories is a stack, but the word stack is so overused, and also, for instance, in moduli stacks, that to speak about perverse stacks would probably be too much. So shopper is simply a stack in German. It's part of general agricultural terminology about sheaves, like sheaves, gerbes, and liens in French. So it's just a word which sort of it characterizes exactly this situation. So let me explain a little bit as an introduction to the concept of perverse sheaves. So suppose we have a stratified space, stratified complex manifold, which means that the manifold is smooth and is represents as union of disjoint locally closed strata. They are smooth, but the closures may be singular. So in this situation, we can speak about constructible sheaves on this stratified space. Like in this example right there, so you have a smooth manifold X, and the complement of this semi-cubic parabola minus the point is a stratum, and the point is another stratum. So we have the concept of constructible sheaves, which are constant on every stratum, and the category of constructible complexes. The complex of sheaves has sheaves of cohomology, and each of them is required to be constructible. Now, inside, we have the abelian category of perverse sheaves, which are actually not sheaves, but complexes, given by some conditions on cohomology. The conditions say that the ith cohomology is supported on codimension I, so they sort of die out in a controllable way. And there's a dual condition, it means that they don't die out too fast. So in a way, one can compare this controllable dying out with the standard concept of a sheaf, which has cohomology only in degree 0. So it's something like a delta function situated at one point, and something like a Gaussian decay, very, very roughly, in the perverse case. So the point of perverse sheaves was that they are self-dual. And again, it's sort of maybe the analogy with the Gaussian function is not so beside the point here. So, and we want to categorify perverse sheaves, to define categorical analogs. So what does this mean? Again, the concept of categorification has been very popular in recent years. It means passing from vector space data to categorical data. And there are basically two guiding principles. So again, categorification is like quantization. It is not a precise term. It is the opposite procedure, decategorification, which is sometimes more clear. So we are talking about, say, triangulated categories, or maybe systems of triangulated categories. It's in a category for two objects, we have the space of morphisms, which is a vector space. In a vector space, for two vectors, we may have a scalar product, which is a number. So it's a passage from numbers to vector spaces to categories. So in a triangulated category, we have a class of distinguished triangles. So for every morphism, it can be included in the triangle. And the third term of a triangle is known as the cone and can be considered as categorical difference. On the level of numerical invariance, that's actually the difference. So, and to a category, we can associate its Grothendieck group which can be made into a vector space, in which we simply impose such relations. For every triangle, the alternated sum is 0. So then we are dealing with the problem of lifting data of vector spaces into data of triangulated categories so that additive relations are lifted in some way into systems of triangles. And remarkable, this structure sometimes suggests itself. So we want to categorify, in this sense, perverse sheaves. But perverse sheaves are not sheaves, they are complexes. If you have the concept of a sheaf, it's not hard, as I said, to generalize it to categories. That's called a stack. One can speak about sheaves of triangulated categories with appropriate enhancements. But speaking about complexes of categories is a little bit, seems unnatural, seems too much. So this, at least now, it is not the way we want to proceed. So a good starting point for this is the direction which has been very active in the early days of perverse sheaves. It's known as the quiver description. It means that we are dealing with an abelian category. And what's an example of abelian category? It's category of modules over an algebra, or representations of a quiver with the relations. So there have been several results saying that the category of perverse sheaves for a given stratified space is equivalent to the category of representations of some quiver with relations. Let me consider the simplest case, when the stratified space is just a two-dimensional disk with one point inside. It means that we are allowed to have singularity and this one point. Outside of this point, everything should be locally constant. So there are two descriptions of the same category. The first one is more classical. It's called the phi-psi description. So this category is equivalent to the category of diagrams formed by two vector spaces, phi and psi, such that identity minus decomposition on both sides is invertible. So this invertible map corresponds to monodromy. So phi is known as the space of vanishing cycles, and psi is known as the space of nearby cycles. So, and in fact, one can give other description, and let me mention one more. With three spaces, it's in a way more symmetric. We have three spaces, E0 and plus and the minus, and now we have some relations, some algebraic relations, some composition like this is the identity, and if you go straight across, it's invertible, and in the other way. So those two quivers with relations, they describe the same category. So the corresponding algebras are Morita equivalent. So, in fact, this description in A, in part A, it categorifies to the concept which turned out to be very important, is concept of spherical functors. It was defined by Anno and Logvinenko following several important previous works. So we have two triangulated categories with appropriate enhancements. So we can speak about cones of maps between functors. And we have a functor U from C0 to C1, and the adjoint functor, U star, V. And we require that, so if it's adjoint, then there is a natural map from, it's called the unit and co-unit of the adjunction. They're natural maps. And if we take cones of them, they are required to be equivalences. So, as I said, the cone is something like categorified difference. So this condition is categorical analog of this condition. But it was not noticed for some time. So in this situation, we can say, just giving an ad hoc definition, that a perverse schober, or categorified perverse sheaf on a disk with singularity at 0, should be simply a spherical form. Now let me discuss what can be possible applications of perverse schobers. Why do we want them? Why do we want to categorify this? So there are three reasons. So first of all, they appear sort of as natural candidates for coefficients for forming Fukaya categories. I'll talk about this a little later. Second, these same structures appear to encode derived categories of varieties related by birational transformations, by flops, also known as conifold transitions in the simple case. Also, they describe categorical analog of Picard-Lefschetz theory, and therefore seem to be related to the famous algebra of the infrared as defined by Gayota, Moore, and Witt. So in the rest of the talk, I will attempt to explain those appearances. So first of all, let me discuss what do Fukaya categories have with perversity. Why have to do with perversity? Why do we need this? So again, it's convenient to sort of have a very far removed bird's view of the subject, and also to compare this with the most naive decategorification of the entire picture. So from a very formal point of view, Fukaya category is a construction which associates to a symplectic manifold, let's say it's compact, a category whose objects are Lagrangian varieties, say smooth and compact, so they are of middle dimension. And the morphisms, it's supposed to be an A-infinity category, so morphism in this category is form a complex, and this is a Floer complex of, in good cases, it's a Floer complex of the Lagrangian intersection, if they intersect transversely. Now already this, if you try to compare this with something familiar, it looks like categorification of a part of middle homology of the manifold. And this sort of corresponds to the intersection form. Also we can say homology or cohomology. In this case, or at least at this level, it is the same. Now, the Fukaya category, unlike homology, is not local because of the pseudo-holomorphic disks used to define the differentials and the compositions. So there has been a proposal by Kontsevich of localization on a singular Lagrangian skeleton. So this proposal gives, or supposed to give an actual sheaf of DG categories on such a singular Lagrangian, so that it's appropriate space of section. It can be called the local Fukaya category, or can be identified possibly with the Fukaya category of the Liouville neighborhood of the skeleton. So it is then defined in more local to global terms, more sheaf theoretic terms, if you like. Now again, this sheaf, if we try to find its analog in conventional topology, this is simply the sheaf of cohomology with support, middle cohomology with support of the constant sheaf. And in good cases, somehow the success of this approach hinges on the fact that this cohomology with support sits in 1 degree. So this one sheaf, which let's call it R, this one sheaf it sort of encodes everything. And it holds in many cases, maybe not for all Lagrangian skeletons, but for those for which computations have been made, this is true. This means that if you take sections of the sheaf, so it should be the nth cohomology with support of your manifold. It's simply the local cohomology. So now, here on the left side, we also have cohomology with coefficients, maybe in a sheaf, maybe in a complex, and so on. And the reason for looking for a similar situation here is the same as the reason for introducing sheaves historically in the first place. Even if we are interested in cohomology with constant coefficients, we may want to study this in the fibration. Similarly, we may want to study the Fukaya category of some manifold using a fibration and using some kind of direct image data on the target of the fibration. But what's important, what is somehow where perverse sheaves shine compared to ordinary sheaves, is that to have such purities, such purity property, F actually should be perverse. So constant sheaf is perverse. But if you just say, if you take some sheaf with singularity somewhere, constructible, it will not be perverse and will not satisfy this condition, that there are no other cohomology. Let me consider an example. So the point is that perverse sheaves, they're better than ordinary sheaves. They're neither perverse nor sheaves, but they're better. So, and in many cases, they do satisfy the purity. So let me consider two examples. First of all, consider the case of a surface. It's a simple example, but if you put coefficients there, that already becomes a non-trivial situation. So suppose we have a topological surface, and we have a constructible complex. Complex constructible with respect to some stratification by a bunch of points. Then, if it's perverse, then for every graph which we draw on a surface, we have only the first cohomology with support. The sheaf, there's only one sheaf of cohomology with support. And this is, in fact, a necessary and sufficient condition. It's a characterization of perverse sheaves. So for ordinary sheaf, it won't be true unless it's constant or locally constant. But for a perverse sheaf, it will be. Another example is when you have manifold is a complex space, and the skeleton is simply the real part of it. And suppose that S is stratification by arrangement of hyperplanes with real coefficients. Something like this. So the space is complex, but on the real part, we still have the arrangement. And again, we have the similar statement that a sheaf is perverse if and only if this cohomology with support is only in 1 degree. So, therefore, so for that, so once again, I'll compare with the previous page. So, for this way of thinking to be successful, it is very natural and desirable to have categorification of perverse sheaves. Yes, so, where did I put it? Yes, so let me discuss the part about which we could work out. Even this is somewhat difficult because when dealing with triangulated categories, in general, dealing with categorical data, there is a question of coherence. And it's somehow the more fundamentally you want to do the coherence, higher coherences, the longer the text becomes. So it is people who work in higher category theory, they are familiar with this phenomenon. But so let me consider the simple situation. Suppose you have a topological surface, and stratification is given. Suppose you have a topological surface, and stratification is given by a bunch of singular points. But the surface, I assume, being allowed to have boundary and the corners in the boundary. So, and for future purpose, I will denote by dx the pure boundary, which means boundary without corners. In this case, we can define the correct way would be an infinity category of schobers, perverse schobers of X with singularities inside this set N. So naively, such a datum would be something like a local system of categories outside this set N. And near every point would be a spherical functor, because a spherical functor describes categorification of a perverse sheaf on a small disk. So, and they should be glued together. So in the local system, we have a monodromy around each point, and spherical functor produces its own monodromy. It is the cone of that map, and they should be glued together in a good way. Now, in fact, one can sort of improve on this definition by producing a more sheaf-theoretic approach. And for this, so we want to have it something like a sheaf. perverse sheaf is not a sheaf, it's a complex. So if you take the sections of over an open set, it's a complex. However, there is certain purity property for perverse sheaves in this situation on surfaces, again, which means that for certain, not individual open sets, but for certain pairs of open sets, we call them Milnor pairs, the relative cohomology of the perverse sheaf will be sitting in 1 degree. And if it's in 1 degree, which means this is a vector space data, and not a complex data, not a data of complexes. So in such pairs, we call them Milnor pairs because they are mimicking the situation of the Milnor fiber of a function. Except here, in one-dimensional, in the complex one-dimensional situation, the function, sort of holomorphic function, is a simple nature. It's a function z to the n. So at the n is some number. So a Milnor pair consists of a disk, topological disk, and call it U, and a sub-open set U prime, which can be disconnected, union of several disks, such that, first of all, the complement is contractible, and here at the end it doesn't quite scan. At most one x in n is inside this contractible thing. So this contractible thing is a thickening of a Lagrangian skeleton. So if we have a perverse sheaf, then it's sort of a sheaf theoretic datum on such pairs. And this goes, it relates to some approach to perverse sheaves that was advocated by Macpherson in his unpublished notes. But so in this case, it's completely elementary. So, and then we can say that a perverse schober is a data of such triangulated categories with natural functorialities, plus certain data for triples. So here, if we have cohomology only in 1 degree, then we have a triple. Then a priori we have a long exact sequence of cohomology of a triple, but if it's only in 1 degree at each point, it's a short exact sequence. And short exact sequence of categorifies to what's known as a recoulement in theory of T structures, or a semi-orthogonal decomposition. So in a sense, a schober would be a data of such categories, plus functorialities, plus a bunch of semi-orthogonal decompositions. So, and then, having given this definition, we have the following result, that such thing does localize on a graph. So if we have something like this, then for every graph, we have a functor from the category of schobers to the category of actual sheaves of categories on the graph, which is compatible by taking Grothendieck groups with functor from perverse sheaves to sheaves on the skeleton. Functor taking each one with some. So, and if a graph is a spanning for this situation, which means that it hits all the corners, it contains the set of singularities, and it's homotopy equivalent to the surface. So the surface has to be open for this. Then the category of sections of this, which we call, is canonically independent on this graph. And this we can call topological Fukaya category with coefficients in the schober. It's of topological nature. So, and it categorifies relative cohomology of surface with modulo boundary with coefficients in a perverse sheaf. Now, let me consider one particular example, what we call a Lefschetz schober. This is sort of a collection of constructions which are familiar in theory of Fukaya-Seidel categories. But again, it's always convenient to first understand the topological analog of this, and then say that what we are doing is a categorification of this topological analog. So suppose we have a holomorphic Morse function from n+1 dimensional Keller-Calabi-Yau manifold to the complex plane. Suppose it's a proper map, has finitely many critical values, so at infinity infinity, everything is okay. Then the standard Picard-Lefschetz picture is that at every critical point, there is a vanishing cycle. So the corresponding fiber has one quadratic singular point. If you move away from this point in some direction, then this point sort of generates, in this direction, a sphere of dimension n. So which conversely vanishing when we go back there. Now, if you use theory of perverse sheaves, it can be formulated like this. We consider the direct image of the constant sheaf under this map. It's a complex of sheaves. It's not a sheaf, not a perverse sheaf. But the perverse T structure, it gives us a way of slicing every complex to perverse sheaves. And so, and those slices are the perverse cohomology sheaves. So this would be the corresponding middle dimensional slicing. It would be a perverse sheaf. And it can be understood like this. So outside of the point A of the critical values, it's simply the local system of the middle cohomology of the fibers. So now, near this point, it's a perverse sheaf on a disk. It's given by vanishing cycles and nearby cycles. So the vanishing cycle, the space of vanishing cycle is one-dimensional and spanned exactly by this thing. Now, this construction, so once we understand it, and it can be categorified to a higher level object, which we call the Lefschetz schober, the perverse schober, which has defined on complex plane the singularities in A. So I recall that outside of the singular point, we have the so-called symplectic connection, which for every path gives identification between the corresponding fibers as symplectic manifolds. So from this one can construct a local system, again, in the higher categorical sense, of the Fukaya categories of the fibers. But near each point, we have the spherical functor. So let me do it again here. So this picture. So we have not just a perverse sheaf, but we actually have a spherical functor, which of course is known in theory of Fukaya categories. It is this object itself, it's a Lagrangian variety in the fiber, which is a spherical object. And spherical object is an example of the simplest spherical functor. A spherical functor from the simplest category, which is the derived category of vector spaces, to the Fukaya category of the fiber. So in this way, we sort of can combine the sort of all analytic information about Fukaya categories of the fibers into one more categorical structure. We call it the Lefschetz schober. And then our result is that if we take Fukaya category, the coefficients in this Lefschetz schober, we get the Fukaya Seidel category. So the only one thing I should say here, that this disk should be considered as a manifold with corners with exactly one corner. So this corresponds to the direction of infinity in Seidel's theory. So, and one can see if we proceed with localization in the graph, we immediately get construction of the category with the semi-orthogonal decomposition. Because locally what happens at every point on the graph is a subversion of the A2 or AN quiver, which produces semi-orthogonal decomposition. But now this is a particular case of topological Fukaya category. We can consider, for instance, a Morse function with values not in the complex line, but in the Riemann surface. Or we can introduce more corners. That would give different categorical constructions associated to this same situation. Now let me discuss another appearance of perverse schobers, which in a way can be said that is mirror symmetric to the previous one, but in the sense in which Fukaya categories are mirror symmetric to coherent derived categories. So I recall that, as I said, the category of perverse sheaves on a disk can be also described by this quiver with three spaces and maps like this, gamma and delta, such that one composition is the identity and going through is an isomorphism. So this corresponds to half monodromies between a point on the left and a point on the right. Now, and this can be compared, so this structure, with the famous birational transformation in three-dimensional birational geometry known as flop or conifold transition. So we consider a three-dimensional quadratic singularity. So it's locally it looks near this point. The manifold looks like a cone over two-dimensional quadric. Two-dimensional quadric is P1 cross P1. So we can blow it up and get a manifold X0 in which this point will be replaced by P1 cross P1. However, this is not a small disangularization. This variety also possesses two equally symmetric small disangularizations when we glue not P1 cross P1, but just a single P1. And we call them, let's call them X plus and X minus. So basically we sort of not blow up, but include this one or include this one, this factor. So in transition from here to here is known as the flop. It's a transformation such that from a three-dimensional manifold, we take away only one-dimensional curve and glue this curve in a different way. So such a situation gives rise to diagrams of coherent derived categories. So the three manifolds are smooth, so there is no ambiguity of what we understood by derived categories. We can take bounded derived categories of those smooth varieties. But it was proved by Bondal and Orlov in 2002 that this thing satisfies those relations, even though at the time nobody looked at this type of description of perverse sheaves, and the relation of perverse sheaves was not noticed. So the relation that some composition is the identity is kind of clear in this situation. But the fact that the going from here to here is an equivalence, we first pull back and then push forward. It was a remarkable discovery, and it gave rise to a lot of developments. So algebraic varieties related by flops typically have equivalent derived categories. So, and since then, similar results were obtained for more general class of flops. I don't go into details, so-called relatively one-dimensional flops of Vandenberg. Now, it's interesting. It's like one can compare this flop to a surgery over a knot. From something three-dimensional, we take out something one-dimensional and glue this one-dimensional curve in a different way. Now, in theory of three manifolds, there is a study of relations between such surgeries, the so-called Kirby moves. So how far can we go? What are the relations among such transformations if we do several things? Suppose we start with this, do a flop, maybe then after this we can do another flop, and so on. So, and this has an analogy in algebraic geometry, studying sort of, one can call it a web of several flops. In this situation, what's, at least for three-dimensional manifold, it is known that the corresponding derived categories, they fit into a local system on appropriate complex space minus appropriate hyperplane arrangement. So a hyperplane arrangement naturally appears in this situation. This comes from ADE classification of singularities of surfaces. So, and this result about local system was found by Donovan and Vips. So this whole direction became a part of so-called homological minimal model program, which studies the effect of flops on the derived categories. So, and we want to conjecture with Bondal and Shechtman that such things, as in that other situation, actually extend to schobers or perverse schobers on the entire CN. So there is data, not just local systems on the generic stratum, but of higher codimension. So to be more precise, if we just axiomatize this concept there, it gets a slightly different concept from the schober as I defined on surfaces before. If you axiomatize this concept, we have three categories, functors like this with relations as I described. However, in that case, we have a little more. We have categorical analog of the cohomology with of individual cohomology spaces with coefficients in a perverse sheaf. We have analog of individual HI. So if a perverse is given by such a diagram, E0, A plus, A minus, then we can write two complexes of length 2, and they calculate either cohomology or cohomology with compact support of a perverse sheaf. So, and we sort of, it's not hard to find the categorical analog in those cases. And our result is that for a flow, for a general flow, as above, in the sense of Vandenberg, the category of sections of this schober is the category of perfect complexes of the singular manifold, and in general, it can be quite singular. It doesn't have to be a quadratic singularity. While the H2 with compact support is the full derived category of the same singular manifold. Now, those two categories are in the relation of duality. This duality was first studied by Bertrand Toyen. So like for vector spaces, we take home to the basic field. And so here we have the category of functors to the simplest category of complexes, the derived category of vector spaces. So in this relation is a kind of manifestation of Poincare duality for perverse sheaves on the categorical level. Okay, so now let me discuss my last subject, which is categorified Picard-Lefschetz theory. So let's just consider any perverse schober in this sense. So I recall that on a disk, a perverse sheaf is given by spaces phi and psi in my first description. So for simplification of what I say, let me now assume that phi and psi will become categories. And so this would be a spherical functor and its adjoint. So suppose we have such a structure. Then at every point, Wi, we have the corresponding category of vanishing cycles. So strictly speaking, it's a local system on the circle of directions. But suppose we choose a direction. Then there's a category phi I and the category psi I, which is a part of the local system outside the singular points. And suppose we have a path gamma, maybe straight, maybe curved, from the ith point to the j point, which avoids all the other points. In this case, we have a functor from phi I to phi j. We're first going by the u functor from phi to psi, then go along the path by translation to the psi, which appears here, and by v functor goes back to the new phi. Yes. So we get such a system of transition functors. So in the example of the Lefschetz schober, when we have a holomorphic Morse function, so there is one vanishing cycle, so this would be a one-dimensional category, so to say, the derived category of vector spaces. So this functor from one such category to another will be a multiplication with some complex of vector spaces. And this complex of vector spaces is the Floer complex for the intersection of two thimples over the midpoint of this gamma. If the gamma is a straight line, then we can simply say that it is space spanned by gradient trajectories of the function, a real part of zeta to the minus 1w, where zeta is the slope of the line. So, but it doesn't have to be, from this topological data, it doesn't have to be a straight line. It can be straight, it can be curved. So now, when we move gamma past a singular point, we have a situation of Picard-Lefschetz theory, which is encoded in the very concept of perverse show. We have exact triangles of functors. We have gamma, or here I forgot to write gamma prime is the next one, when we moved across. Then would be this composition. There is canonical map to the old functor, and the cone of this will be the next one. This is the Picard-Lefschetz triangle, which categorifies the familiar Picard-Lefschetz relations for homology. And this is just basically a feature of perverse schober and nothing else. So this corresponds to the triangle with the monodromy and represented as cone of identity to the composition UV. So now, at the last page, let me discuss possible relation with the work of Guyot and Witten and the algebra of the infrared. I'll recall, again, the situation. We have a holomorphic Morse function. We have a set of singular points. But now we're focusing in particular on straight lines joining those points. And we're focusing in particular on the convexity properties of those objects. We form in particular the convex hull. Now, in this famous paper, Guyot and Witten constructed a Lie infinity algebra corresponding to this set. And A infinity or algebra, or a category RA, plus a morphism from a Lie algebra to the Hochschild complex of this category, which classifies deformations. So, and with Kontsevich and Soberman, we interpreted this via secondary polytopes and proved that this map is actually quasi-isomorphic. Now, moreover, they constructed a Maurer-Cartan element out of appropriate D-bar equation, such that deformation of RA along this element is supposed to be, is conjectured to be the Fukaya-Zyvo category. Now, what we observe in this work in progress with Jan Soberman, that this formalism can actually be developed for any shopper, not necessarily coming from this situation and using the topological structure there. So we will get a similar statement to describe the Fukaya category with coefficients in the shopper if we consider as our base space disk with one core. So the element eta here would come from a system of Picard-Lefschetz triangles. In the simplest case, this element simply corresponds to this map. So this basically shows that perverse schobers appear or seem to appear in many areas. In fact, once you start looking, it seems that wherever you look, you have a manifestation of this categorical structure. And here, so it looks like they they describe some aspects of categorical aspects of what physicists call theories. So, and this it seems to be a very interesting direction, and I think that there can be more applications in the future. Thank you very much.